Swayam Prabha. Digital India. Educated India.
Okay, so what we have discussed in the last class were two types of random walk models. The first one we discussed was the freely jointed chain model, and the next one we discussed was the one dimensional walk, that is the drunkard walk. And what I showed you is in both these cases we are able to recover the relation for the mean squared end-to-end distance as something like proportional to the number of repeat units. Actually what we got was the mean square end-to-end displacement was proportional to the number of segments in the case of a freely jointed chain, and the number of steps the drunkard takes in the drunkard walk. So just to recall, this was my freely jointed chain, and this was my drunkard walk. So I could move in any direction after every segment, and the movement of every segment was uncorrelated with respect to other segments in the system. And though the models look very different, what we realized was that we give rise to the same scaling law for the mean square end-to-end displacement. So now we take it further and try to do some more models, first some more lattice models that will start to look like more elaborate or more realistic compared to the one dimensional walk. But what I want to show you that is give you the same result that we have obtained earlier. So this is where we want to establish the universality in somewhat more detail. Okay. So in the first step, let me talk about what is known as a two-dimensional random walk. Just a simple extension of a one-dimensional random walk. Think of again a drunkard who doesn't know where the last step was. He could have moved to the left or right, and now he can move like again left or right. But now instead of like only moving in one dimension, he can also move in two dimensions, that is like left, right, up, down, or something of that sort. Okay. So let's say for example, this is my 2D random walk. Okay, so let's first look at this 2D random walk, where instead of like one dimensional thing, we have like a lattice, and the walks are happening on a 2D lattice. Okay, so think of like an arrangement of points which is known as a 2D square lattice. Okay. So now again we can start thinking in terms of like steps which are uncorrelated with each other, but now the steps can be either in the x direction or in the y direction. What it really means is the segment vector that we defined earlier, which was in any direction in the freely jointed case, and like plus b unit vector in x direction minus b unit vector in x direction in the one dimensional walk case. So now it can be in any of the available 4 directions where Ex and Ey are the unit vectors in the x and y, and B is again my segment length or step length. Okay. So, again, as the assumption we made here, the probability of each of this to happen was equal. There was two possibilities. So, P was like half in each. Now, in this case P will be 1/4 in all these cases. Okay. And what we can still see in the case is like my end to end distance vector will again be the sum over the bond vectors, where I sum over all the segments. Capital M is the number of segments or steps, and then again I can take the average of this, and by the same logic you can see that the ensemble average of the bond vectors will again be 0, because it can be of course be in the x direction, but it can be in the opposite direction with equal probability. It can of course be in the y direction, but it can also be in the minus y direction with same probability. So, there will be like cancellation of the two vectors. Okay. This is, by the way, is also what is known as the expectation in mathematics. That is, we multiply every possible value with this probability and add them together. If I multiply like each of them by 1/4 and add them together, we will get 0. Okay. And then again the square of this, by the same logic what we had earlier, can be something like this. And again for L not equal to M, this term has to be equal to 0, and for L equal to M, this term has to be B square, because then we are multiplying the same vector, and what it essentially means is we will have the same result, that mean square end to end distance is MB square. Okay. So, although I have showed you for a 2-dimensional square lattice, the same idea will apply for a lattice which in 3 dimensions, actually in any dimension. We can talk about general types of lattices. For example, a 3D lattice will have points in the 3 dimensions x, y and z. Think of like moving on a cubic grid. And now the possibilities will be like, instead of being like 4 in the case of a 2D walk, now the possibilities are actually 6. It can be B unit vector in x direction minus B, the same thing, B multiplied by unit vector in y direction minus of the same thing, similarly in the z direction, and you can see that we will have the same result. Okay. So, in general we can talk about a walk in z dimensions. That would mean that from any particular point on the lattice there are z positions available, and it can move in any of them. Okay. So, you can think of like all possible kinds of walk in this particular way. So, if we have a z dimensional random walk, we have many of these possibilities, which in this case will be like at every point I can go in z possible directions. So, z was equal to 2 for the one dimensional walk, is equal to 4 for two dimensional walk, and is equal to z for a z dimensional. Okay. Z means the coordination number, so as to speak, how many directions you have at any particular point. Okay. So, there is one thing that we have mentioned in passing, that the chain can like fold back into itself. Okay. And what does that mean? So, when for example, I talk about the freely jointed chain, there is nothing that stops me for the next bond vector to be in the same direction as the previous one, just like opposite of it, right. It's going to fold back onto itself. Okay. So, I will answer this question in two ways. First, I will do a case where we allow for the folding back, allow for the folding back not to occur, and then we will try to give some physical understanding of like why does it still work, or what does it actually represent. Okay. So, let us first think of a z dimensional walk or a lattice walk where I do not account for the folding back. That movement is disallowed, and let us see like what happens in this case, because in this case we put in one additional restriction on the next segment. In the earlier cases, all the segments were uncorrelated. Now we are disallowing the folding back. Okay. So, now if I have say a bond vector Bm, the next bond vector can take all the directions except the one that folds back onto it, right. So, if we have say z available directions, only z minus 1 are allowed. Okay. So, we do not allow for the folding back and we look at only the other directions. Okay. So, let us see like what happens in this particular case. So, now if I represent for example A I to be available directions including the one that folds back onto the previous step. So, now if I sum over that A I, this must be equal to 0, because if I account for all the directions, then for every direction opposite direction is equally probable. But now we are disallowing the one that is the minus of Bm. So, Bm plus 1 can take all the directions same as what I have written as Ai except minus Bm. Okay. So, now I can also represent this sum as sum of all the possible values of the Bm plus 1 plus the one that I am disallowing. Okay. So, sum over all possible values of Bm plus 1, which will have z minus 1 terms, and then the one which is disallowed is minus of Bm, because the chain cannot fold back into itself. Okay. So, now if I look at this particular sum, this must be equal to z minus 1 times the average of Bm plus 1, because if I multiply the average by the number of possible values, I should get this particular sum. Okay. But that average now is for a given value of Bm, because if the Bm is changed, then this expression will also change. Okay. So, from this what I can get is Bm is equal to Z minus 1 multiplied by Bm plus 1 for a given value of Bm. What this means is Bm plus 1 averaged for a given value of Bm, this is given, is equal to Bm divided by Z minus 1. Okay. And now let us see like how does it affect our results. So, now again we will have, if I do like Re squared and take its ensemble average, we will have sums of this sort. But now unlike earlier where this value was non-zero only when L equal to M, now this value will be non-zero even for other cases. Okay. And this is because let us say if I try to find Bm dot Bm plus 1, now the Bm and Bm plus 1 are no longer uncorrelated. Now the Bm plus 1 can take all possible values, but the one that folds back into the Bm. Okay. So, now I will use the formula I just derived in the previous slide, the one here on the right, and see that I can write this as something like this, where I multiply Bm with the average of Bm plus 1 for a given value of Bm. So, ultimately this is the average of the product. So, I can move one of the averages inside, and that is what we have done here. Okay. So, now this will be from the formula we have derived Bm dot Bm by Z minus 1, which give rise to B square by Z minus 1. Okay. So, now it is no longer 0. Similarly, if I try to find Bm dot Bm plus 2, I will get something like this, where here I am taking the average of Bm plus 2 for given values of Bm plus 1, and I replace this using the formula we have derived. So, this will be equal to Bm dot Bm plus 1 divided by Z minus 1. We already have seen what the Bm dot Bm plus 1 averaged is. So, this becomes something like B square by Z minus 1 whole square. Okay. So, now you see that we see some kind of correlation between the bond vectors or segment vectors. So, it is no longer 0 for the cases except m equal to L. Now, it is non-zero for the other cases. Okay. But what we see here, if Z is like higher than 2, that is anyway the case, then in that cases this correlation is anyway decreasing as the distance along the chain is increasing. So, between adjacent segments it is B square by Z minus 2, segments which are at a distance 2 apart, it is B square by Z minus 1 whole square. So, in general we can write something like Bm dot Bm plus q will be B square by Z minus 1 to the power q. Okay. Now, let us see like how does it change our change our results. Okay. So let's go back to the formula for RE square and see like how does things change. So now the RE square is sum over m and sum over L, both going until m, and then it is Bm dot Bl. Now there are two possibilities, either the L is higher than m or L is less than m. So let's see like what happens for L higher than m. So for L higher than m, we can represent Bm dot Bl as something like b square by z minus 1 to the power L minus m, because just like we have derived earlier, here the q is like L minus m. Okay. On the other hand, if it is L less than m, then we can write this as something like Bl dot Bm or Bl dot Bl plus q, where q now is m minus L. So what do we see here is something like b square by z minus 1 to the power m minus L. Okay. So in general, what we see here is the power is always positive. When L is higher than m, I will use L minus m. When L is less than m, I will use m minus L. So I can write in general this thing as where I replace the power by the absolute values of L minus m. Okay. And now let's look at like what that sum is equal to. So the way I will do it is I will use the formula for the geometric series. Okay. So in general, what I am writing here, I can write like okay. All I am doing is I am replacing the L by Q as the index, where Q is equal to m minus L. Okay. Okay. So now if I do this series, I can do in variety of ways, but I will make an assumption here, and the assumption is that both these indices L and m, or L and Q in this case, are going to like large values of capital M. Okay. And since this particular term is decreasing with higher powers, it is not much of an approximation if we take this sum from minus to plus infinity, because anyway the higher powers are going to be 0. Okay. So what I will do is I will replace this as something like this, something like that, and then that will be equal to something like that. So, this will correspond to the case when q is equal to 0. When q is equal to 0, then in that case this is equal to 1, this term, and when q is equal to a positive number, then we have a series from 1 to infinity. If q is a negative number, I will have the same series, because in any way the power is absolute value of q. Okay. So, now we can do this kind of a series. This is a simple geometric series, and this will have a value equal to 1 by z minus 1 divided by 1 minus 1 by z minus 1. So, this is equal to 1 by z minus 2. We multiply by 2 here and then we add here. So, the answer we will get eventually will be equal to m b square z by z minus 2. Okay. So, after doing all this kind of a math, what exactly we got? We got like an additional factor of z by z minus 2, which was anyway a constant, because if I go from say a 2D lattice to a 3D lattice or any kind of a lattice, ultimately it is just a number, right. So, it will be like something multiplied by this. The scaling law is still going to be unchanged. Okay. So, this is what we have seen, that the scaling law, that the mean square end to end distance proportional to the number of steps or the number of segments does not change even if we allow for the case when the folding back is not happening. Okay. Now, let us start looking at like what is the physical reason behind this, why is that occurring. And the reason is, if I look at let us say two adjacent segments, these segments actually correspond to carbon chain which have different conformations, right. So, let us say if I look at a polymer model like this, then this in reality correspond to a segment of certain conformation. This will have a segment of some other conformation. So, when the two come together, when this guy sits back on this guy, it is not that the chain of same conformation is sitting on the same conformation, because in that case we can think of like now the electron clouds and everything start to overlap. This is not what is happening. What is happening is like a segment of a certain conformation is overlapping with a segment of a different conformation, right. So, that is the reason why the folding back is not so unphysical, right. What does it mean when the same atom sits on the other atom? That is of course not possible, and that is of course not happening here. All we are saying is that a chain of carbon of a certain conformation is overlapping of the chain of carbon of a certain different conformation. Okay, that is one way to defend our argument. The other way to defend our argument is, why do we care about like what is happening at the molecular level, as long as the final answer is what we intend to get, or as long as the answer that we are getting, Re square proportional to m, is being validated by the experiments, and it is indeed found that many chains do so this behavior. Okay. So, this is called the ideal chain model, just to remind you of the definition. Okay. So, in the next class we will talk about a slightly more detailed model, that is called a freely rotating chain model, and I will show you that again we will establish the same kind of a result. So, the message from here is to demonstrate the whole idea of universality and how does the toy models work in our in the case of polymer physics. So, we can build, I would say, a whole ensemble of different models, and all the models will give you the same result, because it is not that the actual representation of model is affecting the result. It is actually assumptions that we are making in the models that affect the result, and this is what we will elaborate in the next class.